Today's lecture is a continuation of the topic of torsion. So before we continue, a couple questions just to get us back in that mindset. First is, which of the stress components is non-zero? I'm going to say tau, but if I were asking about strain, then gamma would be the answer. But yeah, tau theta z. Okay, so that's the one that's non-zero. And how do we compute that? What's that?
I was going to say RD theta over DD.
No, later in the lecture we have a better equation where we can compute tau with some things that we know.
TR over J.
TR over J, good. So not that we couldn't do it using one of those other formulas, but this is an easier equation because we typically know the torque that's applied and we know the geometry of the member. So it's a simple way for us to calculate shear stress. All right, what is the torque-twist relationship?
TL over J.
Good. So if we calculate TL over GJ or JG, that tells us the change in angle between 2 points as we move along the length of a member. Right? Okay, that is our material relation equation. So it's analogous to our force displacement equation that we had in axial loading. And what is the equilibrium statement for two shafts in series? So that would mean I have a fixed, we'll call this points A, B, C. What is my equilibrium statement?
F1 equals F2 equals F1.
Okay, let's put that in terms of torque. But right, torque 1 equals torque 2. Assuming I don't have a moment applied here at this interface, in the absence of that, the two moments are going to be the same in both specimens. They won't necessarily have the same shear stress, but they'll have the same torque. And what is the kinematic statement for these two shafts? What do we know about the way they displace? Right, so this angle phi, so our angle of rotation on the left side and the right side of the interface has to be the same. Assuming that those two members are solidly connected and there's not any slippage between the two. Slippage will mean that there's a relationship between the two, but they're not equal, that one maybe is 10 degrees more than the other. We might have a slippage of 10 degrees. But assuming there's no slippage, these two are, say, welded together, then as it's rotated, you have the same rotation. So the rotation of B relative to A on the left side of B and the rotation of B relative to A on the right side of B, those have to be the same value. Good. Okay, so let's continue in torsion. Give me just a second. I want to add some extra slides in here. Okay. So last time we talked, we did the example of two shafts in series. Today I want to look at what happens when we have two shafts in parallel. So this will look like this, where we have an outside shaft and then a separate piece in the middle. Perhaps this is a different material. And then we would have bonding all along that outside circumference of the inner member. So along this, I'll highlight it in a different color. All along this circumference, and then along the length, we would have bonding between these two members. And let's say perhaps that this whole thing is fixed at the end on the left-hand side. And then we apply some torque on the right-hand side. So we'll give it a positive torque, like so. Torque. And we know that there are some material properties of these two members. So we will make the outside member, in this case, member 1, which means that that outside member has some G1 and J1 value, and the inside member has a G2 and J2 value, where G is a function, or rather G is a constant that is dependent on the material, and J can be computed using a function that depends on the geometry. And so our question might be asking us to compute the rotation at B, where this left end is A and the right end is B, assuming the rotation at A is 0. Okay, the way we approach this problem is the same as we approach really any problem. We start with equilibrium. So when we have these two members in parallel and we have an applied torque, our equilibrium statement says that the the torque that's resisted by member 1 plus the torque that's resisted by member 2 has to be equal to the total torque applied. So we know that this applied torque is being resisted in combination by the two members, but we don't know necessarily how much resistance is coming from each of the two members. We can't solve that directly from equilibrium, so we're going to need to invoke the other principles of mechanics and materials to get a system that we can solve. So the second pillar is kinematics. Okay, so for kinematics, what do we know to be true about the deformation? Yeah, so more specifically, the rotation of B relative to A for member 1 is equal to the rotation of B relative to A of member 2. And we can just state that as the rotation of B relative to A. Now, that's helpful, but only once we get our third pillar of mechanics and materials written down, right? This equation alone doesn't really do a whole lot for us. It's going to allow us to relate to other things, but right now we say, okay, they're equal, but I can't do much with that. So what brings this all together is our material relations. So when we look at material relations, for the exterior annulus, that's member 1, we say, okay, the rotation of B relative to A, which means the angle at B minus the angle at A, we know that has to be equal to T1 L1 over J1 G1. And for member 2, we know the rotation of B relative to A, which, like I said, is the rotation of B minus the rotation of A, equals T2 L2 over J2 G2. In this particular problem, A is fixed, so we know there is no rotation at A. So that goes to 0. Now we can plug these two equations into our kinematic statement. I can also note that they both have the same length, right? L1 equals L2. So we can cross off that subscript and just use the variable L. And now plugging into the kinematic statement, I say that T1L over J1G1 equals T2L over J2G2. From that, you can solve. You can solve for either T1 or T2 and then plug it into the equilibrium statement to then solve for an actual value for T1 and T2. Once you have those, either T1 or T2, you can plug them into our material relations equations, and what we'll end up with is that phi B equals TL over G1 J1 plus G2 J2. So the way you get that, once again, is by solving this equation for, say, T1, plugging it in here for T1. Now you can solve that. That now will be a function of T2 in two different terms. You solve for the value of T2. You then plug in here for T2, and you're solving for the rotation at B. Questions? So the moral of the story is, on any problem, start with equilibrium, then kinematics, then material relations.
Was that tau on the bottom? Is it tau 1, tau 2, or just T1? Oh, J.
Yeah, in the denominator, those are J's. All right, so now I want to talk about gears. Gears are extremely useful in mechanical engineering, not so much in civil engineering, but being as though we have both civils and mechanicals in here, we're going to cover them for the benefit of the mechanical engineering students. All right, so the way that gears work is that we're going to say apply a torque to one gear, so we're going to try to rotate that gear. And then because there's an interaction between two gears, it will cause the other gear to want to rotate as well. So, for example, we might apply this torque here to gear B. That's going to cause the gear to want to rotate in this clockwise direction. Up here at this interface between the two gears, if there's nothing restraining the motion of gear C will rotate counterclockwise, right? But in this class, what we're interested in is the equilibrium position that it reaches. So at some point, if that gear is connected to, say, a rod that is then connected to some fixed boundary condition, you'll only be able to rotate that rod so far with the torque applied to the first gear. And so that's what we're interested in, is where's that equilibrium position? And so at that point where you stop rotating, what happens is this torque on gear B is met with a reaction force from the other gear. There's some force causing gear B to stop rotating. That has to be equal and opposite to the force that gear B is exerting on this other gear, gear C. So right, you would agree that these two forces have to be equal and opposite. So then, if we have this force Fc acting on gear C, we know that there had to be some moment or torque that was providing that reaction force Fb. And that torque ends up being in the same direction as the applied torque. So the applied torque on gear B is clockwise, this reaction torque, torque C, is also clockwise. Some people have difficulty reconciling that because they feel like gears should move in opposite directions. That's exactly the point. Gears do move in opposite directions. They rotate in opposite directions. But if you're going to stop that motion, you need a reaction that is that is the same. So I always bring things back to axially loaded members, because being from structural engineering, I think better with axially loaded members than I do with twisting members. So if I have, say, this member here, and I apply some force to it, this end wants to move to the right. This left end also wants to move to the right. And then I'm going to have okay, so this, on the right-hand side, it also wants to move to the right, which means that the reaction, this reaction, is in the opposite direction that the motion naturally wants to go. So same thing with the gear. If the motion of this gear naturally wants to go counterclockwise because of the rotation of the gear below, the reaction to stop that motion has to be clockwise. So I don't know if that helps you, but it sort of helps me. Okay, so from this interaction, we get a useful relation called the torque ratio relation. And really, it's just our equilibrium statement applied to gears. So what we say is that if we take the sum of the moment about the center of a gear, that moment has to equal 0. If anything is in equilibrium, you take the moment, you always have to equal 0. So if we're looking at this first gear, the top gear, we have a negative moment from the torque, negative torque on the gear, and a positive moment from the force applied a radial distance away. We know that has to equal 0. Similarly, on the bottom, we have that the torque acting on the gear is going to create a negative moment, and the reaction force is going to create a positive moment. Once again, the reaction is acting a radial distance away from the center. We know that these two forces are the same, right? Equal and opposite reactions. So therefore, I can say that FC minus FB equals 0. And then this equation simplifies to say that the torque applied to one gear divided by its radius is equal to the torque on another gear divided by that radius. And so we use this principle to amplify torques through gears of different radii.
I'm just a little confused about FC, like how it's going in the middle of the gear and on the side, like tangent to the gear.
I didn't, okay. So your question is what's going on with this?
Yeah.
Okay, everything I said, you can think through and accept without those that are circled in green, right? If you just ignore those, pretend they aren't there, everything I said made sense?
Because like they're equal enough.
Yeah, we have our rotation, it has to be met with this reaction force. Okay, so everything made sense, but the reason I show these here is because I'm just precursing to later when we're going to be looking at designing our shafts, is that it's not as simple as just looking at the torque on the shaft. Because if you have this reaction, so if you get this reaction due to the torque in the horizontal direction, if you're just looking at this gear, that gear has to be in equilibrium. If I neglect that force at the center, it is not in force equilibrium. So what that means is that reaction that is resisting the torque, it causes another reaction at the center of that gear on whatever shaft it's attached to. So that reaction is then causing bending in your gear. Bending in your shaft. So you're going to have not only torque, but bending. We're not going to talk any more about that today, but in a few lectures, we will design shafts, in which case you have to look at both bending and torsion. Okay, any other questions about the torque ratio? Okay. Gear ratio. So gear ratio, so that first one, if it relates to equilibrium, this one relates to compatibility. The gear ratio is talking about how these two gears rotate together. So now we do acknowledge that when they will rotate in opposite directions. And that's why I have this negative sign here. That negative sign is to remind us that an angle measured clockwise is the opposite of an angle measured counterclockwise. And so if we were to rotate gear B by some angle that is clockwise, that means that if we started with this point being vertical and we've rotated it, we've rotated that amount of arc length, right? That's the length along the perimeter of this gear that we've rotated. That's given by this function here. Negative just indicating that it's in the opposite direction of the other gear. So for the other gear, we're looking at, it would have started with this point being at the very bottom of that gear, and it's rotated the same arc length, right? They have to, unless the gears are slipping past each other, they have to be rotating the same arc length. And so therefore, the radius of that gear times the angle of rotation has to be equal and opposite to the first. So that's our gear ratio relation. Any questions?
So also this thing means that one gear didn't move without moving the other gear with it?
Right, that they both rotated not by the same angle, but by the same arc length. All right, now we are going to attempt to do an example that involves an indeterminate shaft with two gears attached. So this problem starts out with an indeterminate shaft, so fixed on both ends, and then I put a gear on it. And this is gear 1. And we'll call this point B and point C. And this gear attaches to another gear that we will call gear 2. And that gear is attached to another shaft. Okay. And that shaft can spin freely. We're going to apply a torque over here. So we'll call this point A. And the thing that we're interested in is the change of angle at A due to the torque applied at A. So find the rotation of A caused by the torque at A. So what's happening here is we are twisting that bottom lower rod. The gear is affixed to that rod, so the gear is twisting as well. The direction that we're twisting, our thumb goes towards those arrows, so we're twisting like so, with our fingers going up and over the top. And that means that gear 2 is wanting, the top of gear 2 is wanting to turn into the page. We can twist it a certain amount of distance. We can twist that gear. The rod will twist the gear And we can twist that gear a certain distance, but what's going to happen is that because the top rod is attached, fixed to the two ends, there's a limit to how much we can rotate it with this torque. Right, what you're gonna, that top gear is going to start to want to rotate similarly to the first gear, but because of those two rods, the torque twist relationship will tell us how much those rods can twist before they reach their equilibrium.
So how is TA applied again?
Like that. Your thumb goes in the direction of the arrows. And then we need some lengths on here. So we'll say that from A to the gear locations is L, and then to C is 3/2 L. So I didn't draw it to scale. The way I drew it, it looks like the top gear is right there in the middle, but it should be slightly to the left so that you have 3/2 times L on the right-hand side. Okay, so if we look at, well, let me ask you, where do we start on any problem? Equilibrium. In particular, for torsion problems, we're going to look at equilibrium of the applied torque. So we have the applied torsion at A. TA. And on the other side, so if we take a cut just before the gear, we know that by equilibrium, that has to be the torque on the other side. I can then look at the gear itself. I could look at the gear 2 alone and get that reaction force on the top. So I can go back here. I can look at just a single gear alone and get this reaction force, and then go to the next gear and apply that reaction force and get the torque. Or I can know that we're going to have some relationship to get us directly to that other torque, and instead look at them as one cohesive body that has to be in equilibrium. So that would be my recommendation. I mean, you can do it either way you like, but this would be my recommendation, that you draw both of your gears together. And I didn't state it previously, but each of them has their own diameter. So D1, D2. We know this torque here has to be equal and opposite, so that's going to have the torque applied to that gear is going to be the same as was in the attached rod. And now, the torque resistance in the gear above is going to be split between the rod coming out to the left and the rod coming out to the right. And we know that they have to be the same direction in terms of equilibrium. We know that from this slide here, right? In this slide, TB was clockwise, TC was clockwise. So same thing when we get to this example. These torques, the one that's being applied and the two reactions, they all have to be the same orientation in terms of equilibrium. We'll call this TB and this TC, meaning that those are the torques in the rod between the gear and point B and between the gear and point C. And so that means if I draw this rod here, where this is B, and if I draw this rod here, where this is C, this will be equal and opposite, which means that reaction is there, and this will be equal.
So the two arrows mean into the page?
The two arrows tell you which direction to point your thumb when you're doing the right hand rule for torsion. So for example, this one would be that way and that way. This one would be this way and that way. And that should kind of make sense because this gear, the lower gear, gear 2, it's wanting to rotate kind of up and into the page, which means gear B is rotating out and then down, so out of the page and then down and then back in, which means that you're pulling each of these rods these directions, right? Isn't that the direction that you would be pulling that rod with that type of displacement? And then your reaction, of course, has to be the opposite direction. That's your reaction. So our torque ratio is what we're going to use for equilibrium of this gear. So this is where the meaningful information is where those two gears are applied. And so this tells us that the torque applied to the bottom gear divided by the radius of that gear, say is R2, which of course has to be the diameter divided by 2, has to be equal to the sum of the two torques acting on the top gear. So TB plus TC over the radius of that gear. That's what we can get from that free body diagram. And that will be our first equation. We'll call that equation 1. This is our equilibrium statement. I'll go ahead and rewrite that here. And we know that these are all the same sign, TABC. Okay. So that's equation 1. Okay, so now that we have equilibrium, where do we go next? Compatibility? Oh, what'd you say? Kinematics, same thing. Yeah, potatoes, potatoes. Yeah, kinematics or compatibility are the same. So kinematics. So in this particular problem, is there anything that we know in terms of how these shafts are going to rotate? Yes, we do know that the gears, the arc length of the gears will be the same. Is there anything else that we know about the displacements? In particular, look at shaft BC.
I mean, only VC is going to change it.
There are some stopping points. In particular, B and C are fixed. So what can we gather from that?
Torque should be equal for both parts of the rod.
I don't want to say torque because we're talking about displacements here, but you're on the right track.
Twist.
The twist has to be equal. Or more, maybe same thing, but said differently, is that the sum of the twists has to equal 0. So if you start at point B at a certain orientation, you twist that rod between point B and the gear, that's some twisting that if we were to look at it from this side, we're over here looking this way, that twisting would look as though it were twisting counterclockwise. Whatever magnitude that is, we then need to unravel it by twisting the other direction, that same angle, to get back to C, because initially that shaft went straight across from B to C, and everything was in the same relative orientation. So when you twist it at the gear, you're twisting one direction and then twisting back the other so that it has a net twist of 0. Good. So that's our kinematics observation. So what that says is that the twist of C relative to B is the twist of gear 1 relative to B plus the twist of C relative to gear 1, and that equals 0. And the other thing that you stated was the compatibility. So we said phi1 R1 equals negative phi2 R2. Good.
So twist of 1 relative to B is the same as saying B relative to 1?
It's going in a different direction. So what I've done here, if this is B, C, gear 1, I'm always going from left to right. So I'm saying 1 relative to B and C relative to 1. If you did the other way, if you wrote B relative to 1, that would be going the other direction. You're just going to get the opposite of it. So depending on whether you envision B being held still and you're measuring the rotation of 1 relative to it, or you envision the other, you're going to get a different sign because it'll be either clockwise or counterclockwise, whichever way you're looking at this member. But what I recommend is you position yourself far off in the positive X direction or Z direction, whichever direction is your axial direction. So you place yourself far off in the positive direction, which I'm going to say is over here somewhere past C. Then you look back on the object and you always calculate the nearer point relative to the far point. That way you have some kind of visualization of whether you imagine it being clockwise or counterclockwise, and you're always being consistent. All right, so now we can look at material relations. And we say that the rotation, so the things we're going to write down are going to be for each of the shaft sections. Each section of the shaft will have different rotation. So the rotation of 1 relative to B is going to deal with this section here. So we'll say that, that's not what I want. Say that the torque in that section, which we've defined as torque B, or the torsion in that section. Let me go back to torque. The torque in that section, the applied moment over that section is TB. That section has a length L, and then it has properties G and J. I believe I said all of the shafts have the same G. No, I didn't, but I would like to assume that all of these shafts have the same G and J value, just to simplify this problem. Okay, so that is going to be this, and we know that's actually equal to T1 minus, rotation at 1 minus rotation at B, but we know that rotation at B is 0 because it's stationary. We can do a similar equation for C relative to, for C relative to 1. So that tells us the torque applied to that section times the length. The length is now 3/2 L divided by GJ. This is equal to the rotation at C minus the rotation at 1. And we know that the rotation at C is 0. So that is then equal to the negative of the rotation at 1. So from that, this result, if we take phi1 minus phi1, which is the same as phi1 plus a negative phi1, that has to equal 0, right? Thank you. So phi1 is TB L over GJ plus negative phi1 is TC times 3/2 L over GJ. That equals 0. So now we have an equation that relates TB and TC. We will call that equation 2. So at this point, we have these two variables, TA, presumably with some known value of torque. And now we have a second equation that relates those same two variables. So at this point, we should be able to solve for TB and TC. So the other thing that's relevant, looking at the other thing that's relevant when we're looking at our material relations is we can say that the rotation of gear 2 relative to A. So remember, this connects to gear 2, which then connects to A. So the rotation of gear 2 relative to A is equal to phi 2 minus phi A. And that is equal to the torque that's acting in that section times L, that's the length of that rod, over GJ. Okay. We're going to use this on the next slide. We're going to combine that with this. So these first two, each of the rods has a material relations equation. These first two were useful because we could plug them in to this kinematics equation. This third one is useful because we can plug it into this kinematics equation. So let's do that on the next slide. We have phi 1 R1 equals negative phi 2 R2. And the other equation we had was that the rotation of 2 minus the rotation of A equals TL over GJ. Okay. So I can say that phi 2 is equal to phi A plus TL over GJ. Now I can plug that in so that I have phi 1 R1. And actually we can plug in for phi 1, right? If we go back to the previous slide, phi 1 was found to be equal to this. So we have TBL GJ times R1 equal to a negative phi A plus TL over GJ. Oops. Times R2. Now in this equation, both of the radii are known. TB has already been solved because we had those two equations that had TB and TC, so we could have solved for that. So this left-hand side is completely known. On the right-hand side, we know the applied torque. We know all these geometric values. The only thing we don't know is the rotation at A. So at this point, we can solve for that rotation at A. And if you do that, what you're going to get is that the rotation at A is equal to negative TBL R1 over GJ R2 minus TL GJ. So these are not equations that I want you to memorize by any means. What I want you to get out of this example is how do you set up your equilibrium statements? How do you identify your kinematics relations? And how do you then write out your material relations? Material relations, when we're dealing with torque, always have to deal with a shaft. For equilibrium, we can look at equilibrium of the gears, but those gears never experience the torque twist relationship, right? They just rotate. They don't have a torque twist. But they do give us a kinematic statement in the sense that we can look at the yeah, the surface area that's rotating. I don't know. Chord length, yeah? Arc length. Okay, we can look at the relative arc lengths. And then our material relations, like I said, they always pertain to the shaft. And then the material relations get plugged into your kinematic relations to help you solve these systems. Any questions?
Just if you go back one slide.
Here?
Yeah, so the only thing that confused me was how you decided to start B going to C. So you were B relative to 1 and 1 relative to C?
I did the opposite of that.
Oh,
I did the rotation of 1 relative to B and C relative to 1. You could do it either way as long as you're consistent.
Okay.
So I always chose a point on the right-hand side and measured its rotation relative to a point on the left-hand side. But you could do the exact opposite.
So that's what it means by theta, or whatever that angle, C over B. So
Yes.
now you're gonna have to count for everything in between.
That's looking at the rotation that occurs from point B to point C. So it's and which that means is what you're really calculating is the rotation of point C minus the rotation of point B. And in this case, it consists of two different things added together because there's an intermediary point that changes the behavior of the two sides. And it's really convenient when something is held fixed because then that value defaults to 0. Other questions? Okay, then one last topic I want to get through today, and that is power transmission. So once again, a very important topic for mechanical engineers. And this is looking at the power that we can develop with our torque. Power is a measurement of work over time. Work can be expressed as a force times a distance. So force times distance divided by time. So when we're looking at angular displacements, angular distances, we have the torque multiplied by d phi dt, so times the angular or the derivative of the angular motion. So that is our angular velocity. So our torque times our angular velocity. Angular velocity can be expressed as pi times your frequency times your period. So 2 pi, I'm sorry, I misspoke there. The angular velocity is expressed as 2 pi times the frequency, and then that's getting multiplied by the torque, just like the angular velocity was. So your frequency is the number of rotations per second. Your angular velocity is the derivative of your angle, so your angle of rotation per second. How much are you rotating per second? So when we're designing for transferring power, we solve for the torque. So torque then equals the power over 2 pi f, or the power over omega. That's the relationship that we have. We previously talked about how the allowable shear stress in a member is the torque times the radius divided by J. So we cannot exceed this value of shear stress in our member, otherwise we're going to fail our member. So what that means is that this ratio of C over J, coming from this equation here, that ratio of C over J has to be greater than or equal to the torque over our allowable shear stress. I just divided both sides of that equation by torque. And now if I plug in for torque, P over omega or P over 2 pi frequency, I get these two equations. So I have a relationship between the geometric properties of my shaft and how much power I want to generate and how quickly I can rotate that object, or how quickly I will rotate that shaft. Yes.
So you divide the T to T allowed, but then on the equation on the bottom, it's weird.
Yes, so right here, I'm dividing both sides by T. I see your point. I think that this is backwards. So C over J should equal tau allowable over torque, which then means these must be upside down as well. No, did I do that? I did that wrong. If the torque is on the bottom, the torque is P over omega. So it's like this. So these are flipped. Thank you for pointing that out. All right, with the last couple minutes, I want you to try this problem and then turn it in. We're gonna make this an ICA. So you have a power, P equals 85 watts. It turns at 150 revolutions per minute. So that would be your frequency, right? And I just want you to calculate the maximum shear stress if it's a 20 millimeter diameter shaft. Equation. And torque we said was P this is not F. I apologize. Frequency is in per second. So revolutions per minute. To get omega, you want this to be in radians per second. So you'll need to convert that.